The previous lecture was originally entitled The Sinusoid Source and Response. But if you go and read textbook section 9.2, the sinusoid response, really that section just shows you that if you try to apply these trigonometric functions to circuit elements such as inductors and resistors and capacitors, things get really messy and they get really out of control. But thankfully, there's a notation that we can use to really simplify this process. That's called the phasor, and it's the topic of this really short lecture. In this lecture, we're just going to talk about what the phasor is, and really quickly just sort of derive what the notation means so that we can move on and work some examples with phasors, and then get into the next lecture, which is all about applying these phasors to sinusoidal responses in circuit elements. So let's get into it. Let's start things off by giving us a definition for the phasor. So we'll say the phasor is a complex number which contains the amplitude and phase information of our sinusoidal voltage or current. So, phasor is a complex number. We'll talk about what that means. And it contains the amplitude and the phase information of our sinusoidal voltage or current. It turns out that when we're analyzing the frequency response of circuit elements, the actual frequency, the cycles per second or the radians per second, isn't actually that important. And we can go a long way by just knowing the amplitude and the phase information. So here we're just going to derive a notation that'll basically just make our arithmetic a whole lot simpler and keep us from having to use these complex trigonometric functions that get kind of weird and get out of control. So let's try to derive it just a little bit. And it starts with Euler's identity. Which is that e raised to the plus or minus j theta. Remember, j is the complex number, the square root of -1. Right? In mathematics, they use I to represent this. Since we use I for current, we use j to represent our complex numbers. So that's equal to the cosine of theta plus or minus j times the sine of theta. Now we can take this and break it up just a little bit and say that the cosine of theta is equal to what we'll call the real component of e j omega, and that the sine of theta is equal to the imaginary component of e j theta. This, by the way, is why we choose to use cosine to represent our sinusoids, right? So we can get that real component of our complex number. So if we take this and apply this to the sinusoid that we're used to working with, remember that, for voltage, V is equal to Vm times the cosine of omega t plus phi in volts. If we use this notation, what we can do is say that V in turn is equal to Vm times the real component of e to the j times omega t plus phi. And we can factor in, distribute the j through. And remember, exponents that add multiply, so we're going to rewrite this as v is equal to Vm times the real component of e j omega t times e j phi. Now for the phasor transform, what we're going to do is actually just ignore this e to the j omega t. So we'll call this the phasor transform. This is the part we care about. And it basically says this, that that Vm, the amplitude, times e to the j phi is equal to, sort of this fancy p phasor of Vm cosine of omega t plus phi. There's also an inverse phasor transform. The inverse phasor transform is just this in the opposite direction. We'll say that Vm times the cosine of omega t plus phi is equal to the inverse phasor transform of Vm e to the j phi. So those are our phasor transforms. Now, finally, it is sort of unruly to constantly writing these e to the j phi's when really all we care about is the amplitude and the phase information. So when we go to write everything down, we'll actually use what we call angle notation. Which is basically just this. We have the amplitude, and then this little triangle, and then phi in degrees, and that's equal to ae to the j phi. So there we go. We take the amplitude, the Vm or the Im, and the phase angle, and we just write those as the amplitude, this little angle bracket, and then the phase angle. And that's all there is to it. As you saw, we're going to take the amplitude and the phase angle of our sinusoidal voltages or current and use the phasors, and specifically that angle notation, that really simple angle notation, to capture that amplitude and phase angle information. And as we'll see in the next lecture, we'll actually use that to make our sinusoidal circuit element analysis much more simple, much easier to look at without all that crazy trigonometric stuff. So in the next video, we're going to work an example of how to convert a trigonometric function into a phasor and back, just to kind of put some numbers behind it and see how it actually does simplify stuff pretty considerably. So as always, if you have any questions, comments, or concerns, please let me know. And if not, I'll see you guys in the next video. Thank you.